Hello, I am Themistoklis Melissourgos, and I'm going to present our paper titled Picture Sharing is PPA-hard. This is joint work with Argyrios Deligkas from the Royal Holloway University of London and John Fearnley from the University of Liverpool. This paper deals with mass partition problems. That is, we are given measurable objects in n-dimensional space, and we are asked to fairly divide them according to some fairness criterion. Typically, in the literature appear two main kinds of such problems. One is high dimensional objects that we wish to divide using only a few high dimensional hyperplanes. And the most famous such problem is the ham sandwich problem, where we are given n objects in n dimensional space, and we ask for an n minus one dimensional hyperplane that cuts all bodies in half. And second, low dimensional objects that we wish to divide using many low dimensional hyperplanes. And one not so famous such problem is the consensus halving problem, where we are given n objects in one dimensional space, and we ask for n many zero dimensional hyperplanes, that is, points, that cut all bodies in half. In this work, we study only the second kind of problems, and in particular the following three: consensus halving, straight cut picture sharing, and square cut picture sharing. The mass partition problems fall in a bigger category called fair division, which mainly has been studied by mathematicians in the past and more recently by economists and computer scientists. Sorted by the dimensionality of the resources to be split, some typical real-life problems that fair division tries to model and solve are for one-dimensional resources, radio or TV frequencies; for two-dimensional resources, land mainly; three-dimensional resources, for example, buildings; and high-dimensional resources, which they could be modeling objects that have many attributes, and therefore each attribute is encoded in a dimension, or they could be employed to study existence or computational complexity of low-dimensional versions of the application at hand. In this paper, we focus on fair division of only two-dimensional resources, also known as land division. Let us see through some examples of what ways do we have to our disposal for fairly dividing two-dimensional objects. First, observe that any two-dimensional object can be integrated with respect to one dimension and therefore be projected to the remaining dimension. So, one-dimensional solutions work also for two-dimensional problems, and inductively the argument works for k-dimensional case. Therefore, in principle, we can fairly divide k-dimensional objects using just consensus halving. But let us see an example of this technique. Suppose we have two siblings, B and G, and they have inherited some land from their parents. They want to split this land into two parts such that each of the siblings are indifferent between the two parts. So the blue and red polygons show the areas of value for the agents, blue for B and red for G. The numbers inside the polygons are weights, indicating how much they value a unit of area in the polygon. So let's solve this via consensus halving. We project the two valued regions down to one axis, making one valuation for each of the agents. We then find two cuts here at the bottom of the 0-1 interval that cut these two valuations in half. That is, the value of the white piece is equal to the value of the yellow piece for both agents. Then we extend the solution back to the plane and cut the land accordingly. As you can see, one of the two will have to get two disjoint strips of land in order to be happy. So this is not a solution that we like a lot, but observe that we didn't take into account the dimensionality of the problem. The fact that the objects are placed in two dimensions and not in one gives us more options to cut them. So the question is, can we get advantage of the two dimensions in order to find better solutions? Let's try to use the notion of straight cut picture sharing, where we are allowed to split each of the measures into two equal parts using a single line, but which is freely oriented. And indeed, we can get a nice solution where the assigned piece of each agent is connected without disjoint small pieces. We can also get a nice solution via the square cut picture sharing, where we ask for a corner-like path made of one horizontal and one vertical line segment as shown in the picture. Okay, so again, two solid pieces, one to each of the agents. Let us now revisit all these three solution concepts in the true version, which involves n objects, also called measures, and they partition into two equal parts. So here, each measure is represented by a color. And we will illustrate this with a slightly more complicated example. Now, B and G have their own families consisting of NB and NG people, respectively, and the total number of people is N here. So we want to split each color's area in half. And in our application, this translates to all people believing that the piece their family got is as valuable as the other family's piece. Right, so this is the solution we get via consensus halving, again with many disjoint strips of land, which is not desirable. This is the solution we get via straight cut picture sharing. Here also, each family gets many disjoint subregions, but arguably better than getting strips of land. And finally, via square cut picture sharing, only one family gets 3 disjoint subregions, and so this solution is definitely better than getting several strips of land. Okay, let us now see what was the state of the art on these problems regarding existence of solutions and the computational complexity of finding a solution. In all the following problems, we're given n agents. So for consensus halving, Simons and Su proved via the Borsuk-Ulam theorem that there is always a solution with n cuts. For straight cut picture sharing, Hubbard and Karasev proved recently that there exists a solution with n over 2 lines, rounded up to the next integer. And a few years before that, Karasev et al. Proved that there exists a square cut path that solves square cut picture sharing with only n-1 terms. Now, regarding computational complexity, recently a line of works by Melissourgos et al. Showed that approximate consensus halving is complete for the complexity class PPA, even for inverse polynomial additive approximation, and actually for very simple valuation functions of the agents, namely when they have positive value for only 2 intervals of the 0-1 interval, and the value density is the same in both. So this is called two-block uniform valuation. The problem is also PPA-hard for constant approximation due to another paper by Melissourgos et al. And deciding whether there exists a solution with n-1 cuts is NP-complete. For the exact version of the problem, together with Argyrios a few years back, we showed that the problem is fixed P-hard and in BU, while Baggio et al. Showed that its strong approximation version is BUA complete. Finally, deciding whether there exists a solution with n-1 cuts is EDR complete. Now, in this paper, we mainly show polynomial time reductions from the consensus halving problem to our 2 pizza sharing problems. Furthermore, these reductions obtain the approximation magnitude, and in particular, we get that approximate straight cut pizza sharing is PPA-hard even for inverse polynomial approximation and for very simple objects represented by squares. Now, for this problem, we did not manage to find a reduction for the exact version. Second, we showed that square cut pizza sharing is PPA-hard for inverse polynomial approximation and, again, square objects. Furthermore, we also proved that for measures defined by polygons with holes, the problem is inside PPA as well, and this is also a new existence result. Now, the reduction here also works for the exact version of the problem, in both ways, also the inclusion and the hardness, which yields similar results as those of exact consensus halving. Recently, together with Alexandros Hollander, we improved the inner approximability of consensus halving to constant epsilon, and in particular for any epsilon smaller than 1 over 5, and for very, very simple valuations. So the reductions of the current paper combined with the new approximability yield PPA hardness for the pizza sharing problems for the same constant epsilon. And this is great news since it practically answers a great open question about whether constant approximation of all these problems is easier. But unless PPA equals P, as it turns out, there is no polynomial time algorithm to even approximate solutions to these problems, even for constant epsilon. And here it's worth mentioning another recent result by Schneider, proving that the straight cut pizza sharing problem is PPA complete for point masses. Okay. Now let us demonstrate some of the key techniques for reductions of the approximate versions. We start with the easiest one, consensus halving to square cut picture sharing with overlapping weighted masses. Suppose we have a consensus halving instance as shown to the left. We turn it into a square cut picture sharing instance as shown to the right in the following way. Let us consider as points of interest the points where some of the agent's valuation density changes, either from 0 to positive or from positive to 0. And let these points be m many. The intervals that these points define are called blocks of interest. We create m-1 tiles in the pizza instance such that the total value mass of each agent in the jth block is placed inside the jth tile. We take care of the weight of each agent's measure inside the tile such that her total value mass is the same, and at the same time it fits exactly in the square tile. By doing so, we can prove that such a cut in square cut pizza sharing corresponds to the specific cut in the consensus halving instance, since the portion of mass that the square cut path induces to its right is exactly the portion of value that the consensus halving cut should induce to its left inside the corresponding block of interest. So the line segments of the square cut path alternate between horizontal and vertical. However, this does not change the way they translate back to consensus halving cuts. And a square cut path with n-1 turns, and therefore n line segments, always exists. This is by the known theorem that we mentioned earlier. This translates back to consensus halving solution with n cuts in polynomial time. So the fact that this is an exact translation of the positions of the path segments to cuts permits this reduction to work also for the exact versions of these problems. The second main idea is one that allows us to perform a similar reduction, but for non-overlapping and unweighted masses, which is the easiest instance that one can think of. So again, in consensus halving, we have m points of interest and the induced m-1 blocks of interest. Now, we cannot have masses overlap, so instead we break down what the actual square tiles would be into smaller boxes of inverse polynomial size, the ones we can see in the middle and the rightmost figures. We arrange in a uniform way each of the colors inside the tile such that if a cut passes through a tile in a horizontal or vertical way, it destroys the same portion for all three colors. So placing the colors diagonally basically works. And since the number of small boxes we have created for each color and each tile is so big, the destroyed by the path total mass is at most inverse polynomial because their total mass is very, very small. So by just losing a small fraction of epsilon, you can go back to a consensus halving solution. The third crucial idea is employed by us for the reduction of consensus halving with 2n agents and 2n cuts to straight cut picture sharing with 2n non-overlapping unweighted masses and n straight cuts. So we use again the same idea of points of interest and blocks of interest that are to be turned into big tiles of the straight cut picture sharing instance. Now, the points of interest do not depend on whether there is a change in the evaluation density of some agent, but rather on how many big tiles we want to afford losing as a discrepancy due to the straight cuts. So we have very, very small discretization D, as we call it. Now we place the big tiles one by one on the curve y equals x squared. And inside each big tile lie 2n small tiles in this diagonal way, one for each agent's valuation. You can see 2 consecutive big tiles here and what's inside them. So the distance in the x-axis between consecutive tiles is 6 over d, and this ensures that any straight cut cannot intersect more than 2 big tiles at once. Since there always exists a set of n straight lines that cut the masses in half, this means that the lines will cut at most 2n big tiles, which correspond to at most 2n cuts in the respective blocks of interest, as you can see here. So here are results in more detail. We start with square cut picture sharing. In the first column, we have the class for which the problem is hard. In the second one, we have the epsilon for which the hardness works. And for the PPA hardness, we get constant epsilon due to the aforementioned recent result. In the third column is an upper bound on the number of turns that the square cut path is allowed to have. In the fourth column is the number of disjoint pieces that each measure can occupy on the plane. And finally, in the fifth column is the maximum number of overlapping masses that cover any point of the plane at the same time. So overlap 1 here means no overlap at all. And here are the detailed results for the straight cut picture sharing problem. Again, due to our recent result, PPA hardness holds for constant epsilon. Conclude, we proved that two-dimensional cutting on the plane is not easier than one-dimensional cutting, a fact that is counterintuitive. And this also holds even for very nice solutions that are XY monotone, for example, meaning that they are stairway-like and cut the plane into just 2 solid pieces. Moreover, we provide another 2 natural problems that are PPA-hard and can be used in the future to show hardness of problems in fair division or even computational geometry. And some open questions are the following. Is straight cut picture sharing in PPA? What is the complexity of picture sharing problems for constant epsilon? This is now resolved, as previously mentioned by this paper. What's the complexity of exact straight cut picture sharing? Is it together with square cut picture sharing complete for fixed P or BU? What about the stronger approximation versions? Are they BUA complete, like consensus halving? And finally, it would be interesting to investigate the existence and complexity of solutions for other variants of these problems. 2 intriguing ones are the following. Given a line L and n measures, can we bisect them with n-1 lines parallel to L? Another one is, given a point P and n measures, can we bisect them with n-1 lines that pass from P? So this is all I have to say about this paper. Thank you, and please check the full version on arXiv for any details.